Okay, so for this problem, we want to show that the differential equation is exact. And remember again, this is checking the mixed partials. So for our first term, this is going to be our m, and this is our n. So we want to check the partial of m with respect to y, and then the partial of n with respect to x. So if we take the partial of m with respect to y, we end up with the derivative of x, which is 0. It's a partial derivative again. And then derivative of y, which is 1. And then if we take the partial of n with respect to x, we also get a value of 1 because, again, the derivative of the y is 0. And so because of that, we see that we have two mixed partial derivatives that are equal. So the equation is therefore exact. Okay, so next step is to now find the capital F of x comma y that is equal to c. And remember that the m is already some partial derivative of f with respect to x. So to find the f of xy, we need to integrate m with respect to x. So when we do this, we're going to have our f of x comma y is equal to the integral of x plus y with respect to x. And when we integrate this, we're going to have 1/2 x squared plus x times y plus some unknown function of y that could have been lost in the partial derivative process. So again, this is our capital F of xy. Now we need to use the value of n to make sure we can find g. So now we take the partial of this f with respect to y, which is going to be equal to 0 plus an x plus g prime of y. It's an ordinary derivative because y just is the only variable in g. And again, this must be equal to our n, which is equal to our x minus y. And when you do this comparison, you will always notice that your x terms are going to match perfectly in a comparison, and in essence, they cancel out. So this is going to force the g prime of y to be equal to negative y. And then to get the g, we just integrate with respect to y. And so if we integrate negative y dy, of course we get negative 1/2 y squared. And we do get an arbitrary constant, we'll call it k. So now our f of xy already has the term 1/2 x squared plus x times y, now plus this negative 1/2 y squared plus k. And that is equal to some level c. The next thing we want to do is multiply this whole equation by 2 to simplify it down. So we multiply the whole equation by 2. We end up with just plain x squared plus 2xy minus y squared, and the arbitrary constant k can be combined with the arbitrary constant 2c, and we just get this equal to an arbitrary constant c. So that is the solution of our differential equation. It's going to be x squared plus 2xy minus y squared. And again, just like other problems, we can actually check this solution by going in and taking implicit derivatives and simplifying it down to the original differential equation.